the frequency of sound waves for a monatomic and diatomic system. If the velocity of sound in a solid is of the order of 10 to 3 meters per second, compare the frequency of the sound wave of lambda is equal to 10 angstroms, wavelength of 10 angstroms, for part A, a monatomic system, and part B, acoustic waves and optical waves in a diatomic system containing two identical atoms per unit cell of interatomic spacing 2.5 angstroms. So we have the wave number k 2 pi over lambda, that is 2 pi divided by 10 times 10 to minus 10 meters, that's angstroms. The lattice constant, the interatomic spacing is 2.5 angstroms, that is 2.5 times 10 to minus 10 meters. So if you calculate the wave number k is equal to 2 pi 10 angstroms is 4 times the interatomic spacing, so that's 4a. So this would be equal to pi divided by 2a. And that's basically within first Brillouin zone. Okay. Now the corresponding angular frequency omega is speed of sound times k. We have a linear relationship for the acoustical branch when k is far away from the first Brillouin zone boundary. So that's basically 10 to 3 times 2 pi divided by 10 times 10 to minus 10. This is equal to 2 pi times the frequency. So we see that the 2 pi's will cancel, and we will be left with a frequency of the sound wave 10 to 12 hertz. Okay, now in part B, we're talking about the diatomic system. So we have two identical atoms with mass, equal masses, m and capital M, as we can see here. The distance between two identical masses, d is equal to 2a. So since this is a diatomic system, that's basically the basis. The basis contains the same atoms, but this is the distance between two lattice points. So we have a lattice constant because the distance between two lattice points is 2a. It's basically equal to 5 angstroms. This is going to be twice the interatomic spacing because we have a diatomic basis. So this is twice the interatomic spacing. Now, if we calculate the k value for this wavelength, this is 2 pi divided by 10 times 10 to minus 10 meters. We can see that this is pi divided by 5 times 10 to minus 10 meters, which is pi divided by the lattice constant d. So this basically corresponds to the first Brillouin zone boundary. So if you remember, for a diatomic one-dimensional lattice, we have the Brillouin zone boundary minus pi over a and plus pi over a. So this is in the Brillouin zone boundary. And in the first Brillouin zone boundary, we have standing waves forming. And because of that, what we will see is no sound wave propagation. So even if you look at the acoustical branch or optical branch in the diatomic system, we have the same conclusion because we are at the Brillouin zone boundary. Also, standing waves for the optical branch. So this is our conclusion. There will be standing waves forming and no sound wave propagation as a result. Okay, so let's summarize what we did here. We're looking at the frequency of sound waves for a monatomic and diatomic system. We know the velocity of sound in the solid, and we want to compare the frequency of sound for a wavelength of 10 angstroms for a monatomic system and acoustic wave and optical waves in a diatomic system containing two identical atoms per unit cell of interatomic spacing 2.5 angstroms. Now, if this is a monatomic system, the interatomic spacing of 2.5 angstroms is the lattice constant, and we can see that the K value corresponding to this wavelength, 2 pi over 4a, is pi over 2a. That's within the first Brillouin zone and far from the Brillouin zone boundary. So we know that in this limit where we have a low K value, which is the high wavelength limit, the angular frequency is speed of sound times K. That's for the acoustical branch. So this is basically our linear solution here. So if we multiply 10 to 3 with 2 pi over the lambda wavelength, we find 2 pi times the frequency is 10 to 12 hertz. But for a diatomic system that has two identical atoms per unit cell, so that's a two atom basis, we have the lattice constant 2a. So they have the same masses, but we have a diatomic basis, so basically we can say that we have a lattice constant of 2a. And because of that, if you look at the K value, 2 pi over lambda, that's pi over d, the lattice constant, the new lattice constant, that's the first Brillouin zone boundary. So we will see that there will be standing waves forming and no sound wave propagation. So when we are at the first Brillouin zone boundary, also for the optical branch, we have standing waves forming. So we cannot have any wave propagation.